Hello, AP Chemistry students. It's me, Dr. V, and it seems like a good day to do some review for the AP Chemistry exam. In this webcast, we're going to work through free response question number 3 from the 2023 exam. Now, you probably already know this, but in case you didn't, free response question number 3 on any AP Chemistry exam from the last decade is one of the long free response questions. That means it's scored out of 10 points. And these long free response questions can have 7, 8, 9 different parts to them. They're very long questions, and they can cover a lot of different topics. Before we get started, grab your calculator, have your periodic table, have your formula sheet handy. What I always recommend is that you let me introduce each part of the problem, and then you should pause the webcast and try to answer it on your own. And then listen to my explanation, and then score your work. Did your answer have enough detail to get the point, or did it not? And what can you do to improve your answer the next time? The purpose here really is to show off all that chemistry knowledge you've been working so hard to acquire in the past year, and I want to help you get there. So let's jump right into the problem. Answer the following questions about an experiment in which solid calcium carbonate is combined with hydrochloric acid as represented by the following balanced equation. I've got solid calcium carbonate, I've got hydrochloric acid as my reactants, I've got 3 products, aqueous calcium chloride, carbon dioxide gas, and liquid water. And part A says, write the balanced net ionic equation for the reaction. Now, this is a core skill. You absolutely need to be able to write and recognize net ionic equations. So things to keep in mind here. The calcium carbonate, we're told it's a solid. HCl is a strong acid, and you really need to know that. And you need to know that strong acids dissociate. So when we think about our reactants, we're going to have the solid calcium carbonate. It's going to stay together. It's not soluble in water. And the hydrochloric acid is going to dissociate into hydrogen ions and chloride ions. Notice I have 2 H+, I have 2 Cl-. I need to have conservation of mass and charge. Also pointing out that I need to have H+. It's got to have that ion charge. It's got to be Cl-. And if you don't write H+, or if you don't write Cl-, you've just cost yourself all the points for this question. As I mentioned, the calcium chloride is an ionic compound, but it's soluble in water. It's in solution, we're told that. And so it's also going to dissociate into calcium ions and 2 chloride ions. Chloride are monatomic ions. I've got 2 of them. I have to write 2 Cl-. The carbon dioxide is a gas. It's a molecule. It's going to stay as a molecule. The liquid water is also molecular. It's also going to stay as a molecule. So this is my complete ionic equation. I'm not quite done yet. Looking at the equation, I see that I have 2 Cl- on both sides. Chloride is my spectator ion. I'm going to cross it out. And what's left is my net ionic equation. You don't have to write it out again at this point, unless you really want to, but all that's going to do is slow you down. You don't really have time for that. But this is what you need to have written to earn the point for this question. It's really an all or nothing. Any error, and you won't get any credit. A student performs an investigation to study factors that affect the rate of the reaction. In each trial, the student combines 50 mL of hydrochloric acid solution at 21.2 degrees Celsius with 1.00 grams of the solid calcium carbonate and measures the time required for the reaction to go to completion. The data are given in the following table. And here's the table. 6 trials. I'm looking at this saying, okay, I've got 3 trials at 1 molar hydrochloric acid, another 3 trials at 3 molar hydrochloric acid, and I'm also saying that there are different sizes of the calcium carbonate. I've got a fine powder, I've got small chunks, I've got really big pieces, kind of blocks of it. And then, of course, the last column is the time it takes to reach completion. The student correctly identifies that trial 5 is inconsistent with the other trials. Explain why the student's claim is correct using the data in the table. So we're going to have to compare trial 5, which I've highlighted in blue, to some of the other trials going on. There actually are a couple of ways you could answer this question. Here's my first version. In the first version, I'm going to compare trial 5 to trial 2. All right? Both have small chunks for the calcium carbonate. All right? Trial 5 is a higher hydrochloric acid concentration than trial 2. But when I look at the times, trial 5 has a longer reaction time than trial 2. And this doesn't really make sense. How do I know this? Because if I look at trials 1 and 4, which both have the same particle size, they're both fine powder for the calcium carbonate, and I go from 1 molar to 3 molar hydrochloric acid, having the higher concentration of hydrochloric acid lowers the reaction time. The reaction goes faster. And trial 5 is not consistent with that. So this is one way I could earn the point for this part of the question. Like I mentioned, there's an alternative path you could take to answer this problem. I could compare trials 5 to trial 6. Both of them have 3 molar hydrochloric acid, but here I'm going from the small chunks in trial 5 to a large block or a large chunk in trial 6. But what I see is that trial 5 has a longer reaction time than trial 6. And that's not consistent with other data in the table. If we look at trials 1 and 3, where I have the same concentration, but I'm going from a fine powder to a large chunk, I see that the one with the fine powder has the faster reaction time, a shorter reaction time. So that's obviously related to surface area. And so I could compare trials 5, 6, 1, and 3, or I could do the other. Make sure you're referring back to multiple trials in your answer here. That's really the key point that I want to make. Based on the reaction conditions and the collisions that occur between particles, explain the reason for the difference in the reaction times for trials 2 and trial 3. Now, I kind of hinted at this on my previous slide. If we're looking at trial 2 versus trial 3, they're both 1 molar hydrochloric acid, but I'm going from small chunks or small pieces to a large piece. So I thought, a little T-chart here might be helpful to help me compare the two trials. Trial 2 has 1 molar HCl and small chunks, whereas trial 3 has 1 molar HCl and a large chunk. In trial 2, both trials have 1 gram of the calcium carbonate. That was consistent in all 6 trials. In trial 2, I've got more surface area of the calcium carbonate exposed, whereas in trial 3, with that large chunk, I have less surface area that's exposed to react with the hydrochloric acid. When there's more solid surface area exposed to the hydrochloric acid, there are more collisions between the hydrochloric acid in solution and the solid calcium carbonate, right? This is really all about collision theory. When there are more collisions, reactions go faster. And that's really the key point you needed to make here. If there's a higher number of successful collisions between hydrochloric acid and calcium carbonate in the same time interval, I'm going to make more products. And that's really the gist of what your answer needed to be. All right, so trial 2 needs less time to reach completion compared to trial 3. And it's all about more collisions because there's more surface area. And those are the key points you needed to make here. It was 1 point for more surface area in trial 2 than in trial 3, and the other point for more collisions in trial 2 than trial 3 between the HCl and the calcium carbonate. And that's really the key. The student claims that the reaction is 0 order with respect to HCl. Do you agree or disagree with the student's claim? Justify your answer using the student's data. Remember, justify always means back it up with data, or you're doing some sort of math-based reasoning. Here, we're really going to focus on the data in the table. I'm going to disagree. When I know what the answer is, I like to lead with that as quickly as possible. All right, how do I know this? Well, when a reaction is 0 order with respect to a particular reactant, changing the concentration of that reactant when everything else is constant won't affect the reaction rate. But when I look at trial 1 versus trial 4, so I've got fine powder for both of them, but I'm going from 1 molar HCl to 3 molar HCl. The time changes dramatically. Tripling the hydrochloric acid makes the reaction go a lot faster, which means it's not 0 order in terms of HCl, right? If it were 0 order, I would have no change between trials 1 and 4. Another way you might have chosen to answer this is that tripling the HCl concentration between trials 1 and 4 makes the reaction time drop to 1/3 of its original time. That suggests that the reaction is actually first order with respect to HCl. So you need to disagree, you need to back it up, you need to refer to data in your answer in order to get the point for Part D. Part E says, the hydrochloric acid was present in excess in all trials of the experiment. Determine the molarity of the HCl in the beaker after the reaction is complete in trial 2. Assume that the volume of the mixture remains constant at 50 milliliters throughout the trial. How nice of them to give us the molar mass of calcium carbonate. And if you go back and look at the initial conditions of all 6 trials, we were told we had 50 milliliters of hydrochloric acid in all 3 trials, 1 gram of calcium carbonate in all 3 trials. And the balance equation is going to be necessary here, so I've got that as well. All right, I can't see all of it in the PowerPoint at the same time. So initially, we have a certain number of moles of HCl in trial 2, and we can calculate that, right? I know the volume. I'm going to convert it to liters. I multiply it by the molarity. That gives me 0.0500 moles of hydrochloric acid initially. Similarly, I can calculate the initial moles of calcium carbonate that I reacted in trial 2. I had 1 gram. If I divide by the molar mass, I get 0.00999 moles of calcium carbonate, so just about 0.01 moles. Looking at the balanced equation, it's pretty apparent that we've got a 1 to 2 mole ratio. For every mole of calcium carbonate that reacts, 2 moles of hydrochloric acid are going to be consumed. That 1 to 2 ratio is really important. So I can use that to calculate the moles of hydrochloric acid. It's twice the number of moles of calcium carbonate that I added, or 0.0200 moles of HCl. Since I had 0.05 moles initially, and I reacted 0.02 moles, I'm going to have excess 0.0300 moles of hydrochloric acid. And since we're assuming the total volume is 50 mils throughout the entire experiment, I know the moles of HCl, I know the volume in milliliters, I'm going to convert that to liters, and I'm going to substitute that in. So 0.03 moles of HCl and 0.05 liters of total solution, right? Of course, I've got 3 sig figs for both of those, and I'm going to report a value of 0.600 molar hydrochloric acid at the end of the reaction. This is how I chose to write this out and how I chose to set it up. But if you worked with BCA tables and you want to use a BCA table to solve this, that could also be a great approach. All right, it was 1 point really for finding the moles of HCl that remained, so you had to do the whole subtraction piece. And then the second point for part E was to find the molarity of the HCl at the end and do that correctly and have it be consistent with the moles of HCl that you found. All right, the problem goes on. This is a big kitchen sink problem. In order to measure the enthalpy of the reaction shown, the student repeats trial 1 by mixing 50 milliliters of hydrochloric acid with 1 gram of calcium carbonate using a coffee cup calorimeter. The student records the temperature of the system every 20 seconds, and the data are given in the following table. Okay, so 100 seconds worth of data and measuring the temperature, and I see it goes from 21.20 up to 21.90, and then it levels off. Part F asks, is this reaction endothermic or exothermic? Justify your answer using the information in the table. Well, endothermic processes absorb energy from the surroundings, and that means the temperature of the surroundings will drop. And exothermic processes release energy to the surroundings, and the temperature of the surroundings increases. What I see here is that it's an exothermic process. I'm going from an initial temperature of 21.20 degrees Celsius to 21.90 degrees Celsius. All right, and the difference of those is a positive number, T final minus T initial. As the reaction proceeds, the temperature of the mixture increases, and that's how I justify that this is an exothermic process. And that's 1 point for stating it correctly with a justification that refers to the data in the table. Based on the experimental data, the mass of the system is 51.0 grams, and the specific heat of the reaction mixture is 4.0 joules per gram per degree Celsius. Oh, you know what's coming here, right? Calculate the magnitude of heat transfer, Q, in joules. Well, Q is MC delta T. This is a nice little thermochemistry problem, right? And what do I know? Well, I know the mass of the system is 51.0 grams. I know the specific heat of the mixture is 4.0 joules per gram per degree Celsius. And then I need the temperature change, delta T, which is always T final minus T initial. T final is 21.90, T initial is 21.20. That gives me a delta T of 0.70 degrees Celsius. And substitute them into my equation, and I get an answer of 140 joules. I really only know that to 2 sig figs. I do want to point out that this is being measured for the surroundings. You can't put your thermometer in the actual reaction. We're measuring the temperature change really of the surroundings. And so Q is positive for the surroundings. This is going to be important because I know what's coming next. And that was worth 1 point for a correct setup with a correct calculation and correct answers. Part 2 says, calculate the enthalpy of reaction in units of kilojoules per mole. Include the algebraic sign on your answer. So for part 1 of part G, the sign wasn't important, it was the magnitude. But the sign really does matter, okay? I knew I had 50 mils of HCl, 1 gram of calcium carbonate. We know that calcium carbonate is the limiting reactant. You were actually told HCl is in excess, or we had work in part E to confirm that. All right, so the calcium carbonates are limiting reactant here, and that's going to be something to note, right? And we also know that there were 0.00999 moles of calcium carbonate reacted in each of the 6 trials that were done. So to calculate delta H for the reaction, you're going to take the Q from your previous part and change the sign, negative Q over the moles of the limiting reactant. this is a really helpful thing to remember, because the Q we calculated in G part 1 was for the surroundings, and now we're looking at the system. We're looking at the reaction. So negative Q over moles of calcium carbonate. So we're going to use our answer from part F, but we're going to end up putting that negative sign in because for the reaction, it's a negative value. The reaction has a negative delta H. We're going to divide by the moles of calcium carbonate because that's our limiting reactant. And we're then going to convert it to kilojoules. So I get a final answer of negative 14 kilojoules per mole. I do want to point out we really only know this to 2 sig figs. You never are quite sure which question's being scored on sig figs while you're taking the exam. And all of this was worth 1 point. How did you do? The average score on this question in 2023 was 4.5 points out of 10. So of the long free response questions in 2023, it's the lowest scoring question, but still pretty reasonable question. So if you earned 4 points, you're right on target. If you earned 5, 6, or 7 points, you're doing well. If you got 8, 9, or 10 points, which is reasonable, it's doable on this problem, then you're really doing very well, and you should be pleased. If you found this helpful, like the video and leave a comment, and remember to subscribe to my channel. I'll be recording more videos to help you review for the AP Chemistry exam, so keep checking in and keep studying chemistry.